Can you see my screen?
It's getting there.
Okay.
There
So it's not the slides board, a blackboard. I hope it will work.
That looks nice.
Okay.
Right.
Then I'm gonna slide it like this. I hope this is smooth.
Yes,
okay.
It goes smoothly.
Okay.
All right, Brendan. Let me introduce Eduardo Hoefel from UFPR in Brazil, who will speak to us about Hopf group coalgebras. Eduardo, whenever you want.
Okay, thank you. First of all, let me thank the organizers for this opportunity. And this is a talk, something that I'm still working. It's a work in progress. I'm quite a bit in the beginning of this work. And there may be, I hope not, but there may be some technical conditions that I'm missing in some results. I hope everything is fine, but it's possible, right? It's the first time I'm talking about this. And so the spirit of this talk is like, I'm sharing with you something that I'm still working on. That's the idea of the talk, okay? So there's this notion of Hopf group coalgebras, which was introduced by Vladimir Turayev in the year 2000. And the idea for him was as a tool to construct modular group categories. And this appears in homotopical quantum field theory, okay? So, and here the idea is, okay, let's put aside for a moment the field theory, the homotopic quantum field theory, and let us think just in the algebraic structure, okay? So let's think just in the algebraic structure of Hopf group coalgebras. And the question is, can we build some examples of Hopf group coalgebras using standard or traditional techniques of algebraic topology? That's the question, okay? So, and what's the definition of a traditional technique in algebraic topology is quite a bit confused, but from our point of view, we consider that the cobar construction, okay, the cobar functor or the cobar construction can be considered a traditional technique. And then the question is, can we use the cobar construction to build some examples of Hopf group coalgebras? Okay? So in this talk, we consider a discrete group, pi, and K is a field. Okay? Sometimes, if needed, we can assume that pi is finite, okay? But in principle, it's just a discrete group. So as I say, this concept of that I'm going to introduce now of Hopf group coalgebra were introduced by Turayev and in the year 2000, and Alexis Villesier, he developed much of the algebraic structure in the Hopf group coalgebras. Okay? So in the work of Villesier, you find several algebraic concepts related to this. Okay, so what's a Hopf group coalgebra? Okay, so you take a family. You take a family of vector spaces, okay, over K, and this family is indexed by your group. So pi is your group. Your group is discrete, and each CG is a vector space. Okay, and then you put in this guy you put a graded coproduct, right? So if pi is finite, you can assume that you can take the direct sum of this all these CGs, and it's just a usual coproduct. But if you don't assume that pi is finite, you can also work with this family of deltas here, like that I'm going to show you. So you have a family of delta. They are indexed by pair of elements in the group, okay? And delta G1, G2 goes from the component of the product, okay? So this is the component of my coalgebra, indexed by the product of G1 and G2, and then this guy is taken to the tensor product of the component of G1 and the component of the G2, okay? And this tensor product is always over K, okay? Over the field K, the tensor product. So this family of deltas is co-associative in this natural sense. So you begin with the component of the product of three elements, and you apply delta, okay? And then you break this guy here and here, and here again you apply delta G2, G3, and then you break in these two components here. Okay. If you do the other way possible way in the natural co-associative way, then you get these other three, and the composition of these two maps are the same. So the maps you get from these two processes here are the same. So this is the co-associative. So there should be some tensor product here, maybe. always over K, right? So all my tensors here are over K. So this is the usual co-associative product of property of the product, of the coproduct, but only you are putting it in the integrated complex. You also have a co-unit, but the co-unit goes only from the component of the identity into K. And there's a diagram also for the co-unit, but I don't need to draw it here. It's very natural. You have a co-unit property for this coalgebra, okay? But if you understand well this diagram for co-associativity, you can draw the diagram for co-unit by yourself. It's not a problem. Okay? So you can call this guy, this object, a pi-graded coalgebra or just a pi coalgebra. And if you compare to make the direct sum, you can only think of this guy as this family. Okay. So now what is a Hopf group coalgebra? Okay. You take age. Age is a pi coalgebra. So it's the same thing, same family here, indexed by the group, except that now each HG is a K algebra, okay, over our field K. And all those maps that define the coproduct are K algebra morphism, and also the co-unit map. And then you have a antipode, which is usual in the definition of Hopf algebras, right? Except that in this case, the antipode goes from the component over G to the component over G minus 1. And you have a natural property for the antipode, which is expressed by this diagram here. Okay. So if you apply the antipode as T minus 1 here, and then you do the product in the algebra, because remember, each HG is a algebra, is the same as taking the co-unit and then the unit. Oh, I forgot to say, all those algebras are unit. So they are unit of K algebra. Okay. Then that's the definition of a Hopf group coalgebra. The usual definition of Hopf algebra is self-dual. If you take the dual of a Hopf algebra, is still a Hopf algebra. In this definition, not. So if you take the dual of a Hopf group coalgebra, you get something different, which is a Hopf group algebra, but I don't need to talk about that now. Okay. So one example that you can give, you can do the following. You take a compact Lie group, but not necessarily connected, right? And then you denote bracket A, each component of G, each connected component of G. And A is an element of pi 0 of G. Then this guy is a Hopf pi 0 G coalgebra. Okay, it's not hard to check the details in this example. Problem is that this example is not very interesting, right? Because you can take the component of the identity, right? And then as a K algebra, the cohomology of all of the other components are isomorphic to this cohomology as K algebra, right? And then this cohomology here of the connected component is H0. This guy here, we know that it is a Hopf algebra, right? And then all other components of your Hopf group coalgebra are isomorphic to this. And the coproduct that you can put in this structure it comes from this isomorphism, right? So you have one Hopf coalgebra. Oh, sorry. You have one Hopf algebra here, usual Hopf algebra, and you have a family of K algebras that are isomorphic to this Hopf algebra. So you can put the coproducts that you have here, you can put in this family of K algebras, right? And so the Hopf group coalgebra that you have in this guy is somehow obtained from this structure you have here. So it's not really interesting. It's not something really new, right? So, and then we use this notation. When a Hopf group coalgebra is obtained in this way by this family of isomorphisms, you use this notation. You have a usual Hopf algebra here, and then taken to the power of your finite group or your discrete group. Okay. And then what we want is not this. We want some examples that are not of this type. Then there is this work of Hopf and D'Alembert from, I think it's 2004. I'm sorry about this. It's not 2006, 2004. And I have the references in there. What's the idea of this work? So you can make the definition of Hopf algebras in any symmetric monoidal category. Okay, and if you apply this definition in set, you have exactly groups. So Hopf algebras in set are precisely groups. It's a nice exercise. If you never check this, it's funny. It's interesting to do. And monoidal functors preserves Hopf algebra structure. So if you have different categories and you have something that you know that is Hopf in one category, you can apply a monoidal functor, and then you automatically get a Hopf algebra in another category. That's a very usual idea. And then Hopf and D'Alembert, they introduced this, what they call the Turaev category. Okay, so the objects in this category are families like this. X is just a set, and each mx is a k-vector space. And the morphisms, they are somehow intrinsically contravariant. Okay, and we can discuss why we put this condition later. Okay, but those are the morphisms, right? So the map between the base or set, the index set, goes in one direction, and the morphism between each component of the object goes in the other direction, much like a pullback, right? So intrinsically is a pullback, and we can discuss this later. So they call this Turaev category, they denote by T over K. And you can put a natural tensor product in this category. You just use the tensor product. Remember that here our tensor is over K, but when we generalize to other symmetric monoidal categories, then you just have to be careful which product you are using, but the tensor product is there. And then the result is the following. Hopf algebras in this category are precisely Hopf group coalgebras. So in the same way that Hopf algebras in set are groups, and then Hopf algebras in these Turaev categories are Hopf group coalgebras. If you change the definition, if you don't want this covariance stuff here, you want to keep the same direction in the map between the indexes, then you can do that. Okay? You have another category they call Zunino category, and if you take Hopf algebras in that other category, then you get Hopf group algebras. So there are different definitions. Okay. So then we go on with our ideas, right? You remember that the definition of Turaev category makes sense over any symmetric monoidal category, because you just need this product here, and then this product can be defined in any symmetric monoidal category, and here you keep your set X and Y. Okay, and we can try to use this idea to produce more interesting examples of Hopf group coalgebras. But one thing that you could do is you take the category of, this is just an idea of an example. You take the category of surjective maps, let's say from A to X. Okay, and then the morphism, these are just sets, and then morphisms are commutative diagrams, okay? And then you can check that Hopf algebras in this category are group morphisms, okay? And then you apply a monoidal functor to these objects, and you get another example of Hopf group coalgebras, okay? You have to be careful, because depending on the functor you are applying, you have to make some restrictions over this map for it to be monoidal, okay? But then you can do that. It's not so difficult. You can check, but you have the same problem we have in the beginning. the Hopf group coalgebra that you're gonna create in this by this way is always of this type. So H here is a usual Hopf algebra, G is a group, and you have a family of K algebras indexed by G. They are isomorphic to let me try to be more clear. So you have something like this. But all these HG will be isomorphic to H as K algebras. And the coproduct, the graded coproduct in this object will be inherited or will be induced by this isomorphism. So this example, okay, is fine, but it's not what we want because we don't want examples of this type. We want different kind of examples. So you could use this idea in principle, but again, the examples are essentially the same. So now we try to, sorry about this board. We try to use the cobar functor on pi coalgebras to create more interesting examples of Hopf group coalgebras. So this is work in progress. So the idea is that we will take this functor omega from the category of pi coalgebras to the category of pi algebras. Okay. I have not defined what is a pi algebra, but you can imagine, right? You just have a family A that is indexed by a group G. So each AG is a vector space, and you have a family of multiplications, G1, G2, and with the usual associativity condition, but in integrated context. Okay. So A G1, tensor A G2, to A G1, G2. Okay, so then we have to give this definition. I think I have seen a definition of the cobar functor on graded coalgebras, meaning that this C is an object, it's a chain complex, so it's already graded because it is a chain complex, but also with a grading by a group. And then I searched literature. I think I have seen this some time ago, some years ago, and then I searched literature and I couldn't find where. But I believe that it can be done. Eventually, if needed, we can assume that pi is finite, but I'm not sure if this condition is needed. And you do somehow like this. So you take your coalgebra, okay, your pi coalgebra, and then you create this family, which is supposed to be a pi algebra, okay, in the sense we just described. So each of these elements here should be this direct sum. Remember that not all technical details are checked, but I believe this work. And then you define this tensor product here, right? If G is the trivial group, then what you get is just the tensor algebra, right? So if G is trivial, then omega C is just the tensor algebra over the D suspension C. Okay, then we can put the usual bar construction differential on these objects here, and then we get a, sorry for my board, okay. And we get a pi algebra in the Turev category of chain complexes over K. Of course, we need to check that this is actually differential, right? And the algebra structure on this guy usually and normally, so it's a natural extension of the tensor algebra structure. Okay. you just need to be careful because you are now multiplying things that are indexed by G. So then you have different components, you have different decompositions, but it works. And then it's a pi algebra in the derived category over chain complex. Okay. And then you now can take a object in the derived category over topological spaces. Okay, and then I believe we can define this loop space functor. This is something that I really still working on, but I think I have the definition here. And this guy is a monoid in this category. Sorry, a monoid in this graded sense here. Okay, so you multiply U1 and the 2 in the same way we described before. And I believe that I can prove this version of the Adams theorem for in this context of pi algebras. So here I have the chain complex over each component xg of my graded topological space. Okay, then I put a natural coalgebra structure here using the idea of the Alexander-Whitney diagonal here. Then I put the coalgebra structure here. I do the cobar construction, and I believe I can show that this guy is weakly equivalent to, what is this? So you have to take this loop space definition in this graded context here. And then you take chains over this loop space, and this guy is an algebra. Okay? And the algebra structure here is just induced by the monoid structure in this loop space. Okay? And I believe I can show that these guys are weakly equivalent. As I say, there may be some technical conditions that I need to look more carefully, but I believe I have this result. And I hope to adapt the isomorphism that is present in the paper of Zainalian and Rivera of 2018. They take the cobar construction, take the homology in degree 0, and is isomorphic to the Hopf algebra induced by the fundamental group of X. Okay. So because I have a definition of loop spaces on this graded context, I believe I can define also the fundamental group in that context and extend this result. Okay, but it's something that I'm still working on. Yeah, I think this is it. So, let's say it is just a work in progress, and thank you for the opportunity to give this talk, and somehow it encouraged me to keep further and finish these proofs. Thank you.
Thank you, Eduardo, very much. That was a nice talk. So let's all thank Eduardo. Do we have any questions for him? You should know by now that asking questions is a way to prevent me from asking a silly question. So I do encourage you to do that. You are forcing me to ask a silly question then. I should say that I don't know a lot about all of this, but I'll ask anyway, Eduardo. So you mentioned before how you can always make sense of the notion of Hopf algebra in any symmetric monoidal category. And the kind of silly question maybe is this some sort of group object? Can you think of this as a group object of some sort? Or is that only in some particular cases?
Can you remind me what you mean by group object? Because I'm
Sure. Well, I mean, it can make sense rather restrictedly if you like have a Cartesian product, for example. So you can speak in that particular sense of a group object once you have a Cartesian product. But you can also think of them like by taking representables and asking each of the values, each of those sets to have a group structure. Maybe it's best if I.
Well, if you, I don't know how to answer your question, but if you think in terms of category of sets, right? And then you try to put a diagonal, a coproduct, right? Because you are building a Hopf algebra and you need a coproduct, but you have only one option. I'm not sure if this answers your question, because when you try to put a coproduct with a co-unit, because a Hopf algebra must have a co-unit, then you have only one option for the diagonal. For the coproduct, which has to be the diagonal in set. So each object in the category of set that is a Hopf algebra, then I look at this object as a group.
Okay.
I have heard about group objects in categories,
yeah.
but I confess I don't remember the definition.
Okay.
Some
But
people
yeah,
told me about this, but
yeah.
in my point of view, it's very naive. So each object you have in the category is a group.
Okay. Yes, that's kind of what I was aiming at. So yes.
Okay.
Thanks. Okay. So
yeah, the point is that you have no option for the diagonal. That's it.
Yeah. All right. Do we have any other question for Eduardo? We have 2 more minutes left for questions. Okay. So if not, then let's maybe thank him again for.
Thank you.